Welcome. In this session, we'll learn what's a discrete time system. Let's start. Now, before I discuss what's a discrete time system, let me illustrate what we mean by system first of all. What's a system? So, for a system, formally, a system is simply defined as an entity that has an input, means this system has an input, this system manipulates this input to accomplish any function or any task and thereby producing other outputs. So we can say a system is an entity. Let's suppose this black box is our system that has some input and this system manipulates this input and produces the output. Now from signal and system point of view, what do you mean by system? So from signal and systems point of view, what do we mean by a system? A signal system point of view, system is an entity whose input is a signal. So the inputs to this is a signal or a single signal, and this system or this entity simply manipulates this input signal to perform any task or to accomplish any task, thereby yielding another signal that are referred as output signal or output signals. Simply, right? So what's a discrete time system? Simply then, if the from signal system point of view, if the system is an entity that takes input signals and manipulates these input signals and produces the output signals. Right. So from signal system, this signal system point of view, it's a discrete time system. A discrete time system is simply an entity whose inputs are discrete time sequences. Let's call that sequence x of n, and the output, and it manipulates this input sequence to generate another signal. Let's call that y of n. So a discrete time system is simply an entity whose inputs is a discrete time sequence, which this entity manipulates this discrete time sequence and produces the output sequence. Now you can see this is simply, so mathematically you can say a system is simply a mapping between the values of this input signal to the output signal. So you can also define the system like this. So a discrete time system is simply a mapping between the values of a discrete time sequence to the sequence that's referred as the output sequence, and so it is simply a mapping between the values of one sequence to the mapping of to another sequence. So that's how a discrete time system is defined. Now before I proceed, I want to give you the notation. How do we denote this system operation or simply system mathematically? See, in block diagram form you can use this. You can say if this black box is our system and it's operating on this sequence x of n, and it produces h of n, and we'll denote our system by this capital letter H. Means this system H, when operated on x of n, produces y of n. Mathematically you can write it like this. So y of n is the output of the system H which operates on the sequence x of n. So whether I use this notation or this notation, they are one and the same. So here it simply looks H has input x of n and the output is y of n. In other words, when the system H operates on x of n, it produces y of n. So this is the notation that will follow in this course, right? So let's take some examples of this discrete time system. So if we say y of n is the output of the system whose input is x of n, and this x of n is simply x of n plus x of n minus 1. So what's the system doing? It is simply operating on x of n, and the output is the current sample value of the sequence and the previous sample of value of the sequence. So this is simply summing the values of this input sequence, current sample and the previous sample. Now once we discuss this filter theory, we'll see this will be our low pass filter. So this is simply our low pass filter. Means if you see in the frequency domain analysis. Similarly, another example is so another example of this system notation. Simply system is so what's this doing? This is simply adding the three consecutive samples, means current sample, previous sample, and the next sample of the sequence, and dividing this sum by 3. So this is doing some kind of an averaging. That's why this is also referred as moving averaging filter. This is also referred as moving averaging filter, or simply summer filter. You can say also summer. Right, so this is another example of this system. Now, third example that we can have here is simply x of so this is so when the system operates on this x of n, the output is x of n minus 1. What's this system doing? It's simply delaying the input. It's simply delaying the input by one sample time. It's delaying the input by one sample time, and you can see this is simply a delay, and this can be obtained by simply a flip-flop from digital point of view. You can say this system is simply a flip-flop. Yes, right. So fourth example that we can have about the system is y of n is the output of the system which operates on the sequence x of n, and let's suppose it is doing this operation. So what is the system doing? It's simply taking the cosine of the sample value, cosine of the sample value of the sample value of the signal. It's taking cosine of that. Now let me write a sequence x of n. Let's suppose x of n is simply 2, 1, 3, minus 2 and 1. So this is our sequence. Now if this is the input to the system, calculate the output for system 1, system 2. That's an assignment for you guys. So calculate the output of system 1, example of a system 1 and system 2. Now let's me stop here. In the next session we'll do different classes of these discrete systems. All right, let's end it here.